Dear student, warm welcome to NPTEL Phase 2 program video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This is lecture number 46, Module 9, Geosynthetics for Ground Improvement. I will now focus recap of the previous lecture, that bearing capacity and the settlement, the principle and function of vertical drain, basic principle of prefabricated vertical drain, design chart without and with mere effect. Now, we will continue design chart with mere effect and oil resistance. What will be the design procedure? Step 1, determine the characteristics of soil. That means you should know that what will be the CH, that is coefficient of consolidation for horizontal drainage, that is meter square per second or meter square per month. KH, coefficient of horizontal permeability in undisturbed zone, that is meter per second, and KS, coefficient of permeability in the disturbed or smear zone, meter per second. Step 2, determine the following drain properties, that is dW is diameter of the drain in meter, ds diameter of the disturbed or smear zone in meter, and QW discharge capacity of the drain, that is meter cube per second. Step 3, determine the following consolidation requirement, that is U is average degree of consolidation and T time required to achieve the degree of consolidation. Step 4, determine factor for soil disturbance, that is Fs. So, we will use this equation Fs is equal to Kh by Ks minus 1 into log n ds by dw. Assume ds by dw is equal to 2 to 8. Now, Fs can be determined from this following figure. So, this is the figure is shown that soil disturbance factor Fs versus Kh upon Ks. So, for the defined value of ds by dw, so ds by dw may be 2, 3, 4, 5, 6, 7, 8 like this. So, for the different ds by dw, you can calculate that what should be the soil disturbance factor, that is Fs. So, you know now what will be the ds by dw. If you know ds by dw, also you know what will be the kh by ks. So, knowing kh by ks and ds by dw, then you can calculate what will be the soil distribution factor Fs from this chart. So, I will give you later one example. Now, step 5, determine factor for drain resistance, that is Fr. So, we will use this equation, drain resistance, that is Fr is equal to pi z L minus z into K by QW. What z is equal to distance from the drainage end of the drain, that is meter, L is equal to length of the drain when drainage occur at one drain only, or put L by 2 replacing L when drainage occur from both the end. So, this is the chart oil resistance versus the length, this is the length for defined value of kh by qw, kh by qw 0.001 to 0.002, 0.005, 0.01, 0.02, 0.05. So, knowing the value of kh by qw, kh is coefficient of permeability in the horizontal direction and qw is the flow. So, if you know this ratio of this and what will be the drainage length. So, you know the drainage length, you know the kh by kw, then you can calculate what will be the well resistance factor from this chart, that is f of r. Step 6, determine the required consolidation time T in month and obtain product Ch into T from the following figure. So, here is the product of Ch and T versus the time T. So, you know the defined value of Ch is given here 0.026 square meter per month, like that it is 0.778 square meter per month. So, knowing that time and also this ratio, you can calculate what is Ch into T from this chart. Step 7, determine the parameter lambda from the following figure based on the required degree of consolidation U and Ch into T. So, here product of Ch into and T time T versus the lambda, this is lambda for the defined value of U, that is required degree of consolidation. E value may be 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.95. So, what that here Ch is coefficient of consolidation in the horizontal direction and T is the required time for consolidation. So, this parameter lambda and knowing U and Ch into T, you can also determine this lambda value from this design chart. Now, what is lambda? I will just explain also here that what do you mean by the lambda. So, step 8, add Fs and Fr obtained from step 4 and 5 respectively. So, total Fsr is equal to Fs plus Fr. Now, again F is equal to Fsr plus Fn. What is Fn? Fn is equal to n square by 1 minus n into log n minus 3 by 4 plus 1 by n square, or is equal to log n d by dw minus 3 by 4. Because this n is very small, so n square will be very small. So, we can omit, so we can directly write that log of n means d by dw and minus 3 by 4. So, omitting this value. So, determine the design diameter d in meter from the figure I will show you based on lambda and appropriate FSR for n is equal to 20. Here you know that F of R is equal to oil resistance factor, F of S is mere effect factor, or F of N a shaping factor. This is a Fn shaping factor. So, all combined is gives F is equal to FSR, that means Fs plus Fr plus Fn, Fn means spacing factor. So, it is a combination of the three factors, that is F is equal to oil resistance factor plus mere effect factor plus spacing factor. So, we have observed there are 3 equation for FR, FS and Fn. From this 3 equation you can calculate the 3 different factors, and N is equal to pacing ratio, that is d by small dw, and lambda can be expressed as 8 CHT by log n 1 upon 1 minus u, or is equal to d square into F. So, now this lambda here is the design diameter, that is d in meter, versus the lambda for n is equal to 20, and here that FSR is maybe 0, 1, 3, 4, 6, 8, 10, 12 and 14 for different values. So, knowing also the lambda and FSR, so you can also calculate what will be the design diameter from this chart. Step 9, now find the spacing, that is S. So, you know that D is equal to 1.05 S for triangular pattern and D is equal to 1.13 S for square pattern. So, this above design chart is also developed by Mandal and Fugele 2008, and similar design chart are also developed by Mandal and Sibon 1992 for prefabricated geocomposite drain. As I also mentioned you earlier, that if you know that what will be the horizontal coefficient of the consolidation, and then if you can select the time, whether it is 1, 2, 3 or 4, 6 months, and then you also know that what will be the degree of consolidation, that U value, whether it is 80, 70, 90, 95, and then you can calculate the spacing S. So, there are different design charts also have been made, and for the different prefabricated vertical drain, including natural prefabricated drain. Now, this is one example. Let L is equal to length of the soil strata, about 20 meter, and kh by kh is equal to 5, and ch is 3.9 into 10 to the power minus 1 meter square per month, and ds by dw is equal to 2, and u is equal to 80%, and time t is equal to 11 months. Here to determine the design diameter of the drain influence zone. Now, solution, you know kh by kh is equal to 5 and ds by dw is equal to 2 given. So, from this figure you can see that you know kh by kw. So, kh by kw is equal to 5. So, here is the 5, and then you move up, and then you can check that ds by dw. So, ds by dw is equal to 2. So, this is ds by dw equal to 2, and then you move horizontally towards left. So, you can calculate what is f of s. That means, from this figure you can have fs is equal to 2.9. So, this is 2.9. So, you can calculate fs. Now, you know the length is equal to 20 meter and kh by qw is equal to 0.001. So, from this figure you can calculate what is f of r. So, here is the design length, length is 20 meter, and here is the kh by qw, that is 0.001 kh by qw. So, this is 0.001. So, if you know kh by 0.001, then you move to the left, and then you can calculate what is fr. So, fr is near about 0.9. So, from this chart you calculate fr. Now, therefore, you know that fs r is equal to fs plus fr, that means 2.9 plus 0.9 would be equal to 3.8. So, now U is equal to 80% given, CH into T also 3.9 into 10 to the power minus 1 into T is equal to 11 month. So, that is approximately, let us say, 4. So, from this design chart you can calculate this lambda. So, you know that what is U, 80% you know that what is the CH into T, that is 4. So, CH into T it is 4 here. Then you move horizontally and you require U is equal to, this is 80%, and then you move down and then you calculate what should be the value of lambda. So, lambda here is equal to 20. So, that is why from this figure you can calculate the lambda. Lambda is equal to 20. So, you know FSR is about 3.8 or is equal to 4 and lambda is equal to 20. So, from this figure design diameter of influence, that is D, you can calculate. Now, here that what is the FSR, that means FSR is about 4. So, this is FSR will be about 4 here, FSR 4, and you know the lambda is equal to 20. So, lambda 20, then you move up where FSR is equal to about 4, and then you move horizontally here, then you can obtain that what will be the design diameter D. So, this design diameter of influence D is 1.8 meter, this is 1.8 meter. So, now if you know the D, then you know the correlation between the D and the spacing S for triangular pattern, that is D will be equal to 1.05 into S for triangular pattern and D is equal to 1.13 S for square pattern. So, you can put this value of D and you can calculate the what will be the spacing for the triangular pattern and what will be the spacing for the square pattern. So, you know that how to design that. Ultimately, we have to design what will be the spacing between the two fabricated vertical drain, whether it is a triangular spacing or the square pitting. Now, it is very much essential for instrumentation of embankment on subsoil with prefabricated vertical drain. When you are installing the prefabricated vertical drain, it is required to some instrumentation to observe the behavior of the soil. So, one should know how to and what to place the instrumentation for the embankment on subsoil with PVD. So, this is the initially this marking point, and then you have to install the prefabricated vertical drain. So, this is the prefabricated vertical drain, you are installing like this. So, this is the soft soil foundation and you are installing that PVD like this. So, at a particular spacing, you know how to calculate the spacing between the two prefabricated vertical drain. So, you install, and after that you can provide with the sand blanket. So, this is the sand blanket, or you can place also geotextile or geocomposite material which will act as a drainage. Then after this you have to place the geotextile placement. So, you can place on the top of this geotextile material. Then after this you have to give the instrument installation. You must provide the installation. Here is the instrument you are providing. So, this is the settlement gauge. So, you can measure that what will be the settlement of the embankment. So, you have to provide the settlement gauge. Next, you have to provide the piezometer here to measure the pore water pressure. Then you have to provide with the inclinometer here. Then you have to need the preloading, unit preloading. So you are putting the surcharge load, then there will be dissipation excess pore water pressure, then preloading stage, like 1, 2, 3 stage it is required. So this is, I am telling that this is this PVD spacing, you know, and this is the inclinometer and PVD up to mid depth of the blanket. You should provide the mid depth of the blanket. Here is a blanket. So at least that prefabricated vertical drain should reach to the mid depth of this blanket. So what is the role of the pneumatic piezometer? To monitor the pore water pressure at the desired depth of the compressible soil. Inclinometer, you can measure the lateral movement of the soil at the side slope. Settlement gauge to measure the long term settlement at the original ground surface of the drainage blanket. Settlement plate to monitor the settlement reading. Water stand pipe to monitor the level of water in the compressible soil layer, either in the piezometer or settlement gauge are installed immediately or during the installation of the vertical drain. So it is very important for the instrumentation, and you can measure, and then you can check up what will be the settlement versus time curve. Here it has been shown the settlement versus this time curve. This is the settlement, this is the time, and this is the without prefabricated vertical drain, and here with the prefabricated vertical drain. So you can observe that with the stipulated time, the settlement is more in case of prefabricated vertical drain with respect to without prefabricated vertical drain. So installation of PVD, the vertical drain are available in the form of roll. The band drain or the prefabricated band drain is wrapped around a base plate or a steel bar. I will show you later that what is that steel bar and the base plate at the bottom of the hollow steel lens. The lancey band drain and the steel rod will be pushed into the soft cohesive soil to the desired depth. So it is like, I will show this part, that all push into the soft cohesive soil to the desired depth. When the band drain or prefabricated drain is reached to the desired depth, the lens is to be withdrawn, keeping behind the steel rod and the band drain. So here you can see that installation of the prefabricated vertical drain. This is for to complement to DBM geotechnique, and this is only this one rig, and this very soft soil where the prefabricated vertical drain has been installed. So you can see more the installation of PVD at JNPT for National Highway Authority of India, and this is all white color here. This is prefabricated vertical drain has been installed, and this install about 7 lakhs running meter. These cuts to some foundation. Here is also installation of the prefabricated vertical drain. You can see this is the in the roll form like a roll of huge toilet paper. So this is the prefabricated vertical with this crane, this prefabricated vertical drain inserted to the desired depth, and then on the from the top you can cut it with the help of a scissors. So, this is the installation of PVD at JNPT March 6 India Limited, and installation of PVD about 8,50,000 running meter in 40 days periods. This reported by some foundation. So, here is that how the PVD is joined with the rod, or this is the cross section of the mandrel and the drain. This is the prefabricated vertical drain. Okay. After dictionary detail 1986, or you can use the different base plate. This is the base plate, and this prefabricated vertical drain is wrapped, and then you can stitch or pin, or otherwise you can use a rod. So, to maintain the base of the installation lines. So, this whole thing, this base plate or the rod which where this prefabricated vertical drain is attached, and with the casing or the mandrel, the entire thing will inserted into the soft soil to the desired depth, and then leaving behind this base plate or the rod and the prefabricated vertical drain, then mandrel is withdrawn from the soft soil. So, this is the way that prefabricated vertical drain is installed into the soft clay. So, band-in can be installed very fast. It is prefabricated, lighter, as well as easy to transport and store. It is also economical with respect to the conventional sand drain. The equipment is lighter than the rigs. 15-meter long drain at a spacing of 1 meter to 2.5 meter at a placement rate of 375 meter per hour is possible, as mentioned Hausmann 1990. So, summary of the band-in: geotechnical engineer generally face problem to the construction structure on very soft soil. So, it is necessary to prevent the excessive settlement as well as improve the bearing capacity of soft soil. Therefore, ground improvement techniques are needed. Combination of preloading and installation of prefabricated vertical drain in the subsoil layer can serve the purpose. Prefabricated vertical drain accelerated the consolidation process as well as dissipates excess pore water pressure within a very short period. Now, prefabricated drain have many advantages compared to the sand drain. Rapid settlement of the soft soil is required for construction of the embankment, oil tank foundation, landfill and underwater construction. Sometimes that sand drain may not be continued if the mandrel is withdrawn very fast. Apart from that, due to the surcharge load, there is a possibility for the shear failure of the foundation soil. And in addition to that, as you know, that small diameter of the sand drain offer no shear resistance of the soil. So, you require also initially very low surcharge load in case of the sand drain. So, you cannot put the heavy surcharge load, and also it is very difficult and critical to obtain the material for surcharge onto the spot, and you may require about 10 meter height of the surcharge load, and that is very common. But it is sometimes difficult to obtain the material on the spot, and also it will be very expensive. Now, previdence, but in case of the prefabricated vertical drain, it is efficient and most economical with respect to the sand drain. Now, what will happen between the polymer prefabricated vertical drain and the natural prefabricated vertical drain when you install into the job site? Now, you can see that some differences in the installation technique, that for the natural material prefabricated vertical drain and also the polyester prefabricated vertical drain. In case of the polyester prefabricated vertical drain, when you install the dynamic load, and there is a possibility for the breaking of the core material. But in case of the natural prefabricated vertical drain, if you apply the dynamic load, then core material like a coir or jute will not break. And when you are insulating this prefabricated vertical drain, you do not know that whether the prefabricated vertical drain has been installed properly vertically or not, or what is happening below the ground surface. So, this is the various possibility of the configuration of the vertical accommodation to the soil settlement. So, what may happen that in some cases that if this is the drain and this is the original grade, and this is, let us say, delta of H, and here the relatively the uniform soil mass, and here is the final. So, this drain may be uniformly bending. So, there is a possibility for uniform bending. Or it may if this is the drain, so it may be like this, That means this is sinusoidal bending. This kind of the bending may occur. So, this is the original grade. And this is the final grade. Okay. So, there may be the sinusoidal bending or there may be the uniform bending, you do not know, but this may happen, or it may be, let us say this is delta of H and this drain may be like this, or what you call that local bending. This may be the local bending, and this is the weak zone. Or it may be this is delta of H, or it may be like this. So, here also this is weak zone, and this may be local called kinking. Or it may be, if this is the delta H, or it may be like this. So, this we call the multiply kinking, and this is given by Rollins and Koehner 1988. So, these are the possibility for various configuration of the vertical accommodation for the soil settlement. Maybe we do not know, but there is a possibility this kind of the configuration. So, this is on much more on the research oriented. So, one can observe that what is happening, and that way also some triaxial tests also have been conducted and find out some kind of the kinking of the drain as also observed, because for the kinking that flow of water will reduce, because the cross sectional area also reduced. So, flow of water will be reduced. So, that way this drainage capacity also will be reduced. So, we do not know what is happening below the ground surface, but these are the some possibility for the drain it out. Now, we are showing one example. Compute time required for 60%, 70%, 80% and 95% consolidation at different spacing of prefabricated band drain. Now, the size of the PVD drain is suppose given 100 millimeter into 5 millimeter, and we are considering this is a triangular pattern, and assume that CH value is 6.27 into 10 to the power minus 6 meter square per minute. So, here is the solution. We know consolidation time T is equal to dA square by 8CH ln d by dW minus 3 by 4 into log n 1 upon U. We know that size of the prefabricated drain, that is A is 100 millimeter, width of the band drain, B is 5 millimeter, thickness of the band drain, and dW is the equivalent diameter of the PVD, that is 2 into A plus B divided by pi, means circumference by pi. So, you know the A and B, so you can calculate what is dW. So, 2 into 100 plus 5 by pi, and D is equivalent diameter of the influence, that is 1.05 S for triangular pattern, because we have considered triangular pattern, and S is drainage spacing from center to center between the drain is meter, and CH is given 6.27 into 10 to the power minus 6 meter square per minute. So, here it is shown that this is the prefabricated drain whose length is L of the fabric drain, and this is the A, that is width, and this is the B, thickness. And here this prefabricated vertical drain is placed in a triangular form. You can see this is a triangular form this is a triangular form, like this triangular form, this is a triangular form, and this is a hexagonal, and we assume this as a equivalent diameter. Okay, this hexagonal almost we put it as equivalent diameter, and that is what is D. What is D? So these are the prefabricated vertical den. So in case of triangular pattern, that's why D will take 1.05 into S, and L I say length of the prefabricated vertical den is meter. So here is the spacing either D or S. So you are assuming different value of D or S. Suppose this 2.2 meter spacing, 1.7, 1.43, 1.3, 1.24, 1. So you are assuming different value of D. Okay, average spacing D. D is related with 1.S. Here you are put in S, but you can have in terms of the D. And you have to calculate consolidation time T in month for, let us say, U is equal to 60 degree. I am telling you one factor. Suppose what will be the time for U is 60 degree. So if you can see this equation here, so we know what is D. Let us say D is equal to 1.5 meter spacing. So D, you know, CH value is known, 6.27 10 to the power minus 6, and DW value also you know, because 2 into A plus B by pi, and 2 into 100 plus 5 by pi. So you know DW, you know D, and you are considering for 60% consolidation, then U is 60. So you know 60, you know D by DW, you know CH, you know D, so you can calculate T. What will be the time required? Our target is what time required to reach the 60% degree of consolidation. So here is the table shows that what is the time in month to reach 60% degree of consolidation U with this spacing. So similarly, same spacing if you reach to 70% U, you put this value, so you can obtain this value 6.608. For 80% U, you can have that consolidation time 8.833 month. For 95% U, you can reach this consolidation time is 16.44 month. You can see that degree of consolidation increasing, also that consolidation time also is increasing. And here it has also shown for defined spacing, You can see when you require the lower spacing, let us say 1.05 meter center to center, you can see to reach that 90% degree of consolidation within 3.43 months, 80% degree of consolidation 1.842. Whereas if you keep the spacing more, also you can see your requirement for consolidation time is more. So you require 16.44. So from this table you can also draw a relationship between the consolidation time versus spacing of the prefabricated vertical den under different degree of consolidation. This is a triangular pressure. So this is the time, this is the spacing, this is the E value. So E value 60, 70, 80, 95. So if you want to know what will be the consolidation time required, if you fix up this spacing, then if you want to reach the 95% consolidation, then you will be knowing how many months you require. If you want to reach 60% degree of consolidation, then you will be knowing what will be the consolidation time required. So from this design chart also you can calculate that what should be the spacing between the reinforcement. Here one example is given, the design step for prefabricated vertical den PVD in a runway. So this is one of the project. The subsoil condition, available borehole information show that very soft silty clay exists up to approximately 10 meter to 14 meter below the existing ground level underlain by firm to steep clay. Standard penetration test value N when the very soft layer does not exceed 5, whereas it exceeds 10 in the firm and steep layer. The stratum is found to contain considerable organic material. Area for the proposed runway extension is a low lying area where the groundwater table has been observed close to the ground level approximately 1 meter to 1.5 meter below the existing ground level. You can see that what is the local area. For the construction of the runway and taxiway extension, the existing ground level is needed to be raised by filling about 2 meter to 3 meter. After construction, considerable live load are expected due to the heavy aircraft movement. It is required to improve the very soft subsoil by accelerating its consolidation, thereby increasing its bearing capacity as well. Most cost effective way to improve the underlying very soft clay is installation of prefabricated vertical drain or band drain and preloading. The required drain spacing, time required for consolidation etc. are designed based on the soil characteristic and period available for consolidation. So, preloading requirement consists of the following: A. Load from the pavement. So, concrete is 0.45 meter thick and density 2.4 ton per meter cube. So, this is 1.1 ton per meter square. So, this is the load coming on the pavement from concrete, and GSB layer is 0.90 meter thick and density 1.8 ton per meter square. So, it is give 1.7 ton per meter square. And live load from the aircraft of the pavement estimated is 4.6 ton per meter square. So, total load from the aircraft at the subgrade level is 1.1 plus 1.7 plus 4.6, this will give 7.4 ton per meter square. So, this is the total load from aircraft at the subgrade. So, this is the pavement cross section. So, this is the 450 millimeter thick PQC. Flexural strength is 45 kg per centimeter square at 90 days, and this K value is given 120 Mn per meter cube, that means 12 kg per centimeter cube, and this is 200 millimeter DRLC, this is 350 millimeter, that is WMM, and 350 millimeter GSBC and 200 millimeter sand, and here minimum K is 20 Mn per meter cube or 2 kg per meter cube, and this depth is about 200 millimeter, and from here to here is about 1350 meter. So, solution step 1, calculate the safe bearing capacity of soft soil stratum. You know the equation Q is equal to C into NC divided by Fs, that factor of safety. Q U is the safe bearing capacity ton per meter square, C earned cohesion value ton per meter square, NC value bearing capacity factor value is 5.7 and Fs factor of safety. So, you calculation of safe bearing capacity. So, you put input data, one cohesion is 2.5 ton per square meter and bearing capacity factor is 5.7. So, factor of safety 3. So, you can calculate and you can obtain this factor of safety. Now, this value of safe bearing capacity, so safe bearing capacity is 4.75 ton per square meter. So, safe bearing capacity of the soil 4.75 ton per meter square, but you have observed that your load coming is 7.4 ton per meter square. So, 4.75 ton, what is safe bearing capacity? Less than the 7.4 ton per meter square what is required. Therefore, we have to go for ground improvement because it does not satisfy the bearing capacity of the soil. Now, step 2, calculate the settlement of soft soil stratum using the general consolidation theory. So, you know that delta is equal to CCH 1 plus E0 be log P0 plus delta P by P0, what delta is equal to settlement in meter, CC compression index of soil, and H is the thickness of the compressible clay layer in meter, and P0 is effective overburden pressure at the middle of compressible clay layer in kilopascal, delta P increase in surcharge kilopascal, and E0 initial void ratio of the soil. Now, you have to calculate the settlement, you have put the input data, thickness of the compressible clay layer is 10 meter, height of the embankment is 4.35 meter, compression index is 0.243 and initial void ratio is 1.2 and bulk unit weight of the soil in ton per meter cube 1.7 and unit weight of the embankment ton per cubic meter is 1.8. So, if you calculate, then you can obtain the settlement of the compressible clay layer in millimeter is 563.497 millimeter. So, this is the settlement you have calculated. You calculate bearing capacity, you calculate the settlement. Step 3, calculate the time required for total settlement. So, calculation in earlier step. So, you know that T time is equal to TB into H square by CB or TB is equal to pi by 4 into E square because U is less than equal to 60% and TB is equal to 1.781 minus 0.933 log 100 minus U percentage for U greater than 60%. For T is time achieved required degree of consolidation in month and TB is equal to time factor, H is equal to thickness of compressible clay layer in meter and H for single way drainage layer and H by 2 for both way drainage and CB coefficient of consolidation of soil in meter square per month and U degree of consolidation in percentage. Here you can put the vertical coefficient of consolidation, that is CB in meter square per month is 0.334. Then average degree of consolidation, that is U in percentage, is 90%. So, thickness of the compressible layer H in meter is 10. So, if you calculate using the general consolidation theory, so you can have the design output, that means time required for the given degree of consolidation in year 21.167 and time factor TB is 0.848. So, you see the time required to attain 90% consolidation without any ground improvement is 21.167 years. So, you have to wait more than 21 years to consolidate the soil to improve the ground. So, it is the very critical and difficult. So, step 4, calculate the time required for particular degree of consolidation using PVD. So, you know that T is equal to d square by 8ch ln d by d 1 minus d by d square minus 3 minus d by d square by 4 ln 1 upon u. T is equal to time required for given degree of consolidation, and D is effective diameter of influence for the PBD, that is 1.13 S for square pattern, 1.05 S for triangular pattern, where S is equal to spacing of PBD, and D is equivalent diameter of the PBD, that is D is equal to 2 into B plus T divided by pi, where B is the width of the PBD, T is the thickness of the PBD, and CH is the horizontal coefficient of consolidation. Now, design with prefabricated vertical drain, you can put the design input, horizontal coefficient of consolidation CH in meter square per month 6.7 into 10 to the power minus 1. And average degree of consolidation U is 90%, width of the PBD in millimeter 100 millimeter, thickness of the PBD T in 4 millimeter. So, PBD spacing is in 1.2. So, you can calculate. So, what will be the time required for the given degree of consolidation with PBD in month 1.62, and time required for the given degree of consolidation with PBD is 1.81 when there is a square pattern, and earlier one when there is a triangular pattern. So, effective diameter of influence of PBD D, that is for triangular pattern, is 1.05 into spacing, that is why it gives 1.26, and for 2 for square pattern is equal to 1.13 into spacing, that is 1.356. So, in triangular pattern, time required for 90% consolidation with PBD is 1.52 month, that is for 45 days. In square pattern, the time required for 90% consolidation with PBD and 1.81 month, that is 55 days. So, you can complete this consolidation using the prefabricated vertical drain within 45 days if it is a triangular pattern, and 55 days if it is a square pattern. Step 5, calculate the required height of the embankment that can be safely placed on subsoil stratum. So, H shape is equal to QU by gamma of soil. H shape is equal to height of the embankment that can be safely placed on subsoil stratum in meter, and QU is the shape bearing capacity of the soil is 4.75 ton per meter square, and gamma soil unit weight of compressible soil is 1.7 ton per meter cube. So, you can calculate what will be the height of the embankment that can shape the place, that is height H shape is equal to 4.75 by 1.7, that means that is 3 meter. Step 6, decide the number of the stages and days required for application of embankment loading in such a manner that the total number of the days D should be greater than the days required for the discharge settlement using the prefabricated vertical drain. Step 7, determine the improvement in initial cohesion and thus shear strength in each stage. So, CU increase divided by delta P is equal to 0.15 plus 0.0045 into Pi in percentage into U by 100 percentage. So, Cu final will be Cu initial plus Cu what is increase. So, Cu that final will be Cu initial and Cu increase will be equal to this into delta P. So, this into delta of P. So, what Cu increase is the increase in the initial cohesion. You know what will be the initial cohesion there. Then after that, what will be the cohesion after the improvement, that is Cu of final. So, what will be the increase you know. So, you can calculate what should be the cohesion after the improvement. So, Cu initial is given 2.5 ton per meter square, where U is desired degree of consolidation 91%, 55% and 33%. And Pi is the plasticity index of the soil, is 27%, and delta P is the increase in overburden pressure. That means is equal to height of the field into field density. Field density is given 1.8 ton per meter cube. So improvement in cohesion due to consolidation in stage 1, that means Cu final will be equal to 2.5, that is initial cohesion value, plus 0.15 plus 0.0045 into this 27, that means plasticity index 27 into that U value 91 by 100, this into that is the 3 into 1.8, that means 3 is the height and density is 1.8, that is why 3 into 1.8. So this will give you that is delta P, that means delta P is equal to 3 height and density 1.8. So 3 into 1.8. So C of U final will be 3.83 ton per meter square. Now improvement in cohesion due to consolidation in stage 2. So Cu final will be, now initial is 3.83 plus 0.15 plus 0.0045 into 27 into, now these are degree of consolidation 55 by 100 into 4 into 1 point, delta P will be equal to 4 into 1.8. So this will give the Cu final 4.91 ton per meter square. Now improvement in cohesion due to consolidation in stage 3. So Cu final is, this is 4.9 plus 0.15 plus 0.0045 into 27 into 33, the degree of consolidation, 33 by 100 into 5 into 1.8 delta P. So this is delta P. So this will give the 5.7 ton per meter square. So you observe that improvement of cohesion due to consolidation stage 1, consolidation stage 2 and the consolidation stage 3. So with this I finish my lecture today. Let us hear from you any question. Thanks for listening.